for kind introduction, Dr. Amir. It is a pleasure for me to talk to the international and multidisciplinary audience here. And thank you very much for the organizing committee to invite me to give this talk. My talk title is How to Increase the Catalytic Efficacy of Platinum-Based Nanocatalysts for Hydrogen Generation from the Hydrolysis of Ammonia Borane. I would like to draw your attention to a big threat for our planet, namely global warming. The ice core data in the graphic shows that both the average temperature, blue line curve, and the atmospheric carbon dioxide concentration undergo parallel variation, both decreases first over 100,000 period, decreases first slowly, gradually, and then one observes a sudden increase in both values and decreases again periodically. Okay. However, after the last period, both of them do not decrease. They remain at the top. Even carbon dioxide concentration continue to increase. So these are the result of ice core data. I would like to show the recorded data. The temperature on the Earth's surface has been recorded since 1850 about, or 1854. And as one can see from this diagram graph, the temperature, average temperature increases continuously since then. So in the last century, the increase, relative increase is about 1 degree or more than 1 degree Celsius. That's huge, and it is going to continue. And let's look at the recorded carbon dioxide concentration in the atmosphere. So the carbon dioxide in the atmosphere has been recorded or measured since 1956, exactly. And you can see that the average value of carbon dioxide concentration increases exponentially. And today, the concentration is almost 420 ppm. So the result is, because of the carbon emission from the combustion of fossil fuels. So carbon dioxide is emitted into the atmosphere from the combustion of fossil, mainly from the combustion of fossil fuel, and therefore the carbon dioxide concentration increases. And I want to show, just tell the amount of the carbon emission annually a year. So it is 10 metric tons of carbonyl, 10 billion metric tons of carbon, 10 billion. And when you convert this one to the carbon dioxide, it is more than 40 billion metric ton per year, 44 billion metric ton. So the global warming is obviously due to the emission of carbon dioxide from the combustion of fossil fuels. That is the problem. What is the solution to that problem? Is to replace the fossil fuels by renewable energy sources on the way towards a sustainable energy future. Okay, is there any problem? Yes, there are two main problems in that way. One is the high cost of the energy generation from the renewable energy sources, which needs to be reduced, lowered, that energy cost. And research is going on that topic. The second problem is the discontinuity in the energy production from the renewable energy sources, like solar energy, wind energy, and so on, which requires storing energy. In that context, hydrogen is going to play a vital role for this transition from fossil fuel to the energy, renewable energy sources. There are many problems, but first of all, hydrogen can be generated from various sources, because hydrogen we don't have any hydrogen resources, just the H2 gas, hydrogen gas, I mean, and therefore that hydrogen must be generated. And it can be generated from various sources. And hydrogen can be used also in many ways. That's good, many ways. So-called the hydrogen economy contains research and development in three topics: production of hydrogen. As I said, there are research going on produce hydrogen from various sources. And also for the use of hydrogen, we have to be able to use hydrogen in as many ways as possible. But hydrogen is gaseous, and therefore it is not safe and efficient to store hydrogen in gaseous state or liquid state. And therefore, solid hydrogen storage materials are required. There are many options, but the most promising solid state hydrogen storage material is ammonia borane. Ammonia borane with catalyst, this one. Ammonia borane. So ammonia borane is the most promising solid hydrogen storage materials. It has very high content, hydrogen content, almost 20%, and it is stable in solid state and also in solution. And it can release hydrogen from its hydrolysis. Here you can see the reaction. It releases 3 equivalent hydrogen per mole of ammonia borane from that hydrolysis. But that hydrolysis can occur only in the presence of catalyst. Without catalyst, it doesn't. It is stable. And transition metal nanoparticles are the most commonly used catalyst in this reaction. But noble metal particles are the highest activity catalyst. And among them, platinum is one of the most active transition metals, providing high turnover frequency for releasing hydrogen from ammonia borane. However, high price of this precious metal, platinum, hinders its large-scale application in catalyzing hydrolysis of ammonia borane. So we have to solve that problem. The challenge is the enhancement of the efficiency of platinum catalyst, or we can say utilization efficiency, catalytic performance, and thus ultimately lowering the cost of platinum catalyst. So I will show that there are issues in this concern. The first one is the achieving high catalytic performance with the smallest ratio of platinum to ammonia borane. As you know, the catalyst to substrate ratio in catalysis is very important parameter. It should be as low as possible. So for the platinum in ammonia borane, that ratio, platinum to ammonia borane ratio, should be as small as possible. That's one way. Or making as many platinum atoms in the catalyst as possible to be active site. So in a solid catalyst, only the surface atoms are active. The atoms in core are not. So that means we have to try to keep the surface atoms as high as possible and no inactive core atoms, if possible. Increasing the stability and lifetime of nanocatalyst, in that case, platinum nanocatalyst, and making the platinum catalyst reusable. That's also important. We should not use just once. The platinum nanoparticles or catalysts, we should be able to reuse them. So the first approach is the use of platinum nanoparticles, colloidal platinum nanoparticles as catalysts. So colloidal nanoparticles are active catalysts because of the large surface area of colloidal particles. So because of the large fraction of surface atoms, so that large fraction of the active sites, and therefore colloidal nanoparticles are usually much more active than compared to the bulk metal. So the first try was done in 2007. Colloidal platinum nanoparticles were obtained from the reduction of hexachloroplatinate, and gradually and becoming active as the nanoparticles are formed, as one can see from the hydrogen generation plots. So nanoparticles are slowly formed and then increases the activity, and the activity getting higher activity, the hydrogen generation rate increases, and one can measure the highest rate, hydrogen generation rate in that linear region, and which can be converted to the TOF value, turnover frequency. It provides, that should be minute, sorry about that, 600 reciprocal minute, the TOF value. Okay, however, they are not stable. These nanoparticles, colloidal nanoparticles, are not stable because there is no stabilizing agent in the system. Just the chloride anion, which is a very weak stabilizer for the platinum nanoparticles, and therefore they are not stable and therefore not reusable. So how can we make the nanoparticles stabilized? There are a few ways. One of them is by adding the stabilizing ligands into the solution. And the stabilization will depend on the nature and the concentration of that stabilizing agent. In this study, polyvinylpyrrolidone has been used as stabilizer, and nanoparticles are obtained quite stable. We don't know actually how stable they are. They have never tested, but it's active. The nanoparticle, platinum nanoparticle is active. However, the activity is less than that of colloidal platinum, bare colloidal platinum nanoparticles. So instead of 600, they observe 492 because of the stabilizing agent covers the surface and the activity is reduced, lowered. And as I said, the stability and reusability have not been tested, unfortunately, in that study. The second approach is the immobilization of platinum nanoparticles on a solid support with large surface area to stabilize them against agglomeration. So one of the support material is carbonaceous ones. Carbonaceous materials can be used as support for the platinum catalyst in many carbonaceous materials like carbon nanotubes or graphene, reduced graphene oxide, and so on can be used. So one interesting point I want to show is that they studied the in situ or ex situ preparation of platinum nanoparticles on the surface of carbon nanotube. And one can see that the nanoparticles, platinum nanoparticles of the same size can be formed either in situ or ex situ preparation technique. That means in situ during the hydrolysis of ammonia borane. That means the reducing agent is ammonia borane and slow reduction, while in the ex situ, sodium borohydride has been used somewhere else and prepared the nanoparticles and then bring the nanoparticles. Is there any problem? I was warned that the connection is unstable. Okay.
No, sir,
is there any problem?
No, sir, we can hear you well. Please.
Okay. And however, the in situ and the ex situ nanoparticles, prepared nanoparticles, have different loading, 1.5% platinum or 6.0 platinum loading, and therefore the activities are expected to be different, of course. And indeed, they are different. The ex situ provides 400 top reciprocal minute, while the in situ only 100. But something is weird here, so it should be opposite actually. And therefore, I don't want to rely on that result. Anyway, the ex situ and the in situ are different. Another work has been done by Ozkar. Dendrimer, platinum nanoparticles are stabilized in dendrimer. These two types of dendrimer, they provide quite high activity, but still it is far away from the colloidal nanoparticles. Okay? The activity is low. Conclusion here, the use of carbonaceous supports can provide a certain escalation in activity of platinum nanoparticles, maybe because of the large surface area. However, the catalytic activity is lower compared to the colloidal nanoparticles. Platinum nanoparticles on the surface of carbonaceous support are not stable because the weak metal support interaction, obviously, even functionalization of the surface of carbon nanotube makes only minor contribution to the strengthening of metal support interaction, and therefore it is really not usable. And reusability of platinum nanoparticles on the carbonaceous support has never been reported. However, the recyclability tests show considerable activity loss in consecutive cycles. So I will conclude that the use of carbonaceous materials for the hydrolysis of ammonia borane is not the way to go. The other way to stabilize the nanoparticles, to support them on the oxide nanopowders. Different oxide nanopowders with relatively large surface area have been tested. Silica, mesoporous silica, titania, we have done this titania work. Ceria, tungsten oxide, tungsten 6 oxide, and organic metal, organic framework, and silica, and so on. However, the use of oxide support does not lead to a noticeable enhancement in the catalytic activity of platinum nanoparticles in hydrolysis of ammonia borane, probably because of the relatively small surface area. The stability and reusability have never been investigated. There are two exceptions to this generalization. One is the cobalt 2,3 oxide, cobalt oxide, and the other one is the cobalt ferrite. I will talk about that in a minute. The third approach is the downsizing the platinum nanoparticles. So downsizing the particles causes a notable increase in fraction of surface atoms, and therefore in the catalytic activity of nanoparticles. In colloidal system, the particle size can be determined by nature and concentration of the stabilizing agent. Unfortunately, there is no paper reporting the catalytic effect of particle size on the colloidal nanoparticles, and depending on the stabilizing agent and this concentration, because the increasing concentration of stabilizer is expected to reduce both the particle size and the catalytic activity, as the active site on the surface become less accessible due to the surface coverage. In the case of supported nanoparticles, it has been shown that the reducing particle size causes an increase in the catalytic activity of nanoparticles. Here is the example. Platinum nanoparticles supported on cobalt ferrite. The particle size has been changed by increasing the platinum loading from 0.23% to 0.48 to 1.95. And particle size increases from 2.3 to 2.4 to 2.6, slightly increases. And one can see that as the platinum loading increases, particle size increases, but the activity decreases. From the top value, you can see here, activity decreases with the increasing particle size. Or we can say downsizing the particles, reducing the particle size, increases the catalytic activity, top value, and enormously, as you can see, from 435 in that study to 1959 reciprocal minutes, the activity increases. Another approach to use is the single atom platinum catalyst in the hydrolysis of ammonia borane. In the extreme case, the supported single atom platinum maximize the atom efficiency because we have just single platinum atoms supported on a surface. And that should be highly active, and it is actually. It is a result of a study. Single atom platinum nanoparticles, or single atom platinum catalysts, I should say, have been generated on this graphene, zirconia, ceria, and cobalt oxide. As you can see, cobalt oxide is superior in terms of activity. Also, in terms of reusability or recyclability, in that case, is also very outstanding, I should say. The activity in the graphene platinum, single atom platinum on graphene decreases very quickly. The same for zirconia and also for ceria, decreases rapidly first. However, in the case of cobalt oxide, single atom on the cobalt oxide, the activity remains, actually, I should say, more or less within 10% variation. Okay. This is attributed to the metal support interaction, which is confirmed by the binding energy of platinum in the XPS. So only cobalt oxide supported platinum, single atom platinum has very high binding energy, as high as platinum 4, while the others have lower binding energy. Another study is the single atom platinum nanoparticles, single atom platinum in the nickel particles, which are supported on the either carbon nanotubes or CTF or activated carbon and so on. So here you can see the result of on the carbon nanotube in that case, as the platinum is doped in the nickel particle, the activity increases. Here we can see much better. That is platinum. The purple one is the top value of platinum on the carbon nanotube. So as the platinum concentration or doped concentration is about 1/100 of nickel, the activity is maximum, but there is some variation. One cannot understand this one. Anyway, but the doping the platinum increases the catalytic activity. That is important. However, we will see that the conclusion is not really correct, because when when we talk about the platinum in the nickel particles, that platinum cannot be considered as a single atom, because platinum is surrounded by the nickel atoms. Maybe we can consider as an alloy in that case. So nickels are certainly interacting with the platinum. That means that platinum cannot be considered as a single atom, and therefore the activity should not be assigned to the platinum alone. It should be assigned to the nanoparticles, the whole nanoparticle, platinum plus nickel. And therefore, I don't want to discuss that one more. But there is another problem. The catalytic activity of single atom platinum nanocatalysts is intrinsically limited by the amount of platinum, which cannot be increased without agglomeration. When we increase the platinum amount or content, the platinum will be close to each other and they can agglomerate very easily. They can interact with each other. And therefore, the use of single atom platinum nanocatalysts seems to be tough in large scale application. In general, single atom metal nanocatalysts are attained if the metal ligand interaction will be stronger than metal-metal bond. Otherwise, we should not be able to get the single atom. Metal experiences aggregation, even under mild condition. We have to remember that such a strong metal support interaction might cause reduction in the catalytic activity as well, because a tightly bound metal atom may be less accessible by substrate molecules. The fifth approach is the increasing the reusability and lifetime of platinum catalysts. So there are two parameters which can be used to increase the catalytic efficiency. rising the lifetime and increasing the reusability of the catalyst. Lifetime is a useful parameter for evaluating the catalytic efficiency, which can be measured by using a prolonged recyclability test. Unfortunately, it has never been performed or reported for the platinum-based catalyst in hydrolysis of ammonia borane. The reusability is mainly determined by the isolability or separability of the nanocatalysts for subsequent uses. Low reusability is because of material loss during the separation of nanoparticles from the reaction medium for reaction solution, either by filtration or centrifugation, and redispersing in the solvent for the next run of catalysis. During all these processes, materials will be lost, certainly unavoidable, I should say. Okay, how can we avoid that? Making the nanoparticles magnetically separable. That will be nice. So that is the sixth approach, actually, making the platinum nanoparticles magnetically separable, nanocatalysts. So nanoparticles can be supported on the surface of a magnetic core, and that means the nanocatalyst will be separated by using an external magnet. So in the case of cobalt ferrite, platinum can be impregnated, platinum precursor can be impregnated on the surface of magnetic core and reduced by sodium borohydride to form the nanoparticles on the surface of the magnetic core, nanoparticles. So here we can see the nanoparticles on the surface of the magnetic core, magnetic cobalt ferrite, and the particle size distribution has been studied and the XPS. So these nanoparticles show superb catalytic activity, 3,600 reciprocal minutes. That's huge, actually, at room temperature. That's a high or record activity at that time. And because they are magnetically separable, we can recover the nanoparticles after the catalytic from the solution, catalysis from the solution, and then redisperse it in a new batch of reaction solution and do the reusability test. And you can see that after 10 runs of reusability test, the activity remains essentially the same. There's almost no change in the activity after 10 runs. So the superior catalytic activity and stability of the magnetically recoverable platinum cobalt ferrite nanoparticles are attributed to the favorable interaction between the platinum nanoparticles and cobalt ferrite surface as elucidated by XPS. I didn't show the XPS, but one can see that the interactions. The outstanding reusability is due to the magnetic separability of the nanoparticles, as well as their stability provided by the favorable metal support interaction as elucidated by XPS again. Metal support interaction is quite strong in that case, and therefore they are reusable. The nanoparticles are reusable. Another magnetic material, cobalt oxide. Cobalt oxide can be used as support for the platinum nanoparticles exactly in the same way, and one can obtain platinum nanoparticles on the surface of cobalt oxide nicely, and they are very active. Let me see whether I have the activity here or not, but they are very high activity. But here, as you can see, there is no leaching from the support to the solution during the hydrolysis reaction. So platinum nanoparticles show superior catalytic activity even greater than that of cobalt ferrite, 4,360 reciprocal minutes for hydrogen generation from the hydrolysis of ammonia borane. That high activity can be attributed to the favorable interaction between the platinum nanoparticles and cobalt oxide surface, which we have studied by XPS analysis. So cobalt ferrite is magnetic, or became magnetic, and therefore we can use the magnetic separability of the materials to investigate the reusability, which shows very high reusability. After 10 runs, there is no sign for decrease in activity and conversion either. That means even after 10 runs, 100% conversion, that means 3 equivalent hydrogen per mole of ammonia borane is obtained with the activity same as initial activity. So let me conclude my presentation. The catalytic activity of platinum-based catalysts can be increased by using nanoparticles. However, there are still work needed to be done in this topics. Downsizing the nanoparticles, supporting the nanoparticles on the material with large surface area, stability and lifetime platinum catalysts can be increased by selecting support which provides favorable metal support interaction, as we have shown by using cobalt ferrite and cobalt oxide. The reusability of platinum nanoparticles can be significantly increased by supporting them on the surface of magnetic powders, by making them magnetically separable. That is the most important result which we have. Catalytic efficiency in general of platinum-based catalysts can be increased by a suitable combination of all of these approaches. So we should not rely only on one, rather we should combine them to get high catalytic efficiency. And I thank you for your kind attention.